We now have all the pieces to define the FFT algorithm. Let's start with the high-level idea of the algorithm once again. We're given a polynomial a of x. We're given this polynomial by its coefficients. Let's assume this polynomial is of a degree at most n minus 1, where n is a power of k. And we want to evaluate this polynomial at endpoints. Now in the end, when we do polynomial multiplication, we actually want this polynomial a of x at two endpoints. In order to obtain it at two endpoints instead of endpoints, we can just pad the polynomial, the coefficients, with zeros, so that we view the polynomial as a degree 2n minus 1 polynomial. Now what are the endpoints that we're going to choose? We're going to choose the nth roots of unity as our endpoints, which we're going to evaluate the polynomial a of x at. Now since n is a power of 2, so n equals 2 to the k for some positive integer k, then we know that these endpoints, the nth roots of unity, satisfy the plus-minus property. So the first n over 2 are opposite of the last n over 2, and the other property is that the square of the nth roots are the n over second roots. Now we're going to take this polynomial a of x, and we're going to define a pair of polynomials, a even and a odd. We take the even coefficients, and that defines this polynomial a even. We take the odd coefficients of a of x, and that defines this polynomial a odd. And the degree of these two polynomials is at most n over 2 minus 1. So we went down from a polynomial of n minus 1 degree to two polynomials of degree at most n over 2 minus 1. Now what we saw earlier is that in order to obtain a of x at these endpoints, we need to evaluate a even and a odd at the square of these points. So what we do is we recursively evaluate a even and a odd at the square of the nth roots. What's one of the key properties of the nth roots of unity? It's that the square of the nth roots equals the n over second roots. And there are n over 2 such roots. So in order to obtain a of x at endpoints, we need to evaluate these two polynomials, a even and a odd, of half the degree at n over 2 points. So we got two subproblems of exactly half the size. And these subproblems are of the same form. We want a of x at the nth roots, a even and a odd at the n over second roots. Finally, given a even and a odd at these n over second roots, it takes order n time to get a of x at the nth roots. We simply use this formula from before. A of x equals a even at x squared plus x times a odd at x squared. So it takes order 1 time to compute a of x for each x, and there are order n x's. So it takes order n total time to compute a of x at the nth roots of unity. Finally, what will be the running time of this algorithm? Well, for the original problem of size n, we defined two subproblems of size n over 2. We recursively solve those to get the polynomials a even and a odd at the n over second roots, and then it takes us order n time to merge the answers to get a of x at the nth roots. This is the common recurrence that you've seen many times, probably for merge sort and stuff like that, and this solves to order n log n. And this is the sketch of the algorithm to take a polynomial in the coefficients form and return the evaluation of the polynomial at endpoints, where the endpoints are the nth roots of unity. And it does so in time order n log n.